Good afternoon, students. My name is Olga Polomarchuk, and I will be one of your lecturer. And today we have our first lecture, which is the resting membrane potential, action potential, and the mechanisms. So here we have a plan of today's lecture. So the first topic that we are going to discuss is physiology as the theoretical basis for the medical profession, resting membrane potential and mechanisms of its establishment, action potential and its ionic mechanisms, graded potential and its features, mechanism of conduction of the action potentials, and types of nerve fibers. So let's start with the first subtopic. And first of all, I would like to explain you what is it physiology and what are the questions that gives answers this subject. So physiology is a branch of medicine that studies the function of the human body, the underlying physiological processes, and mechanisms of their regulation. Let's explain three important terms that are explaining physiology. These are function, underlying processes, and regulating mechanisms. So function can be defined as the achievement of a desired outcome for the body. So let's have a few examples. So, for example, the function of the heart is to provide a closed loop circulation of blood through the vascular system. Function of the lung is to provide gas exchange between blood and the external air. And, for example, kidneys, function of the kidney is to purify the blood from toxins by urine excretion. And so on for many other organs. Every organ have its own function. But if you look more closely at the function of each organ, you can see that all these functions are achieved by the interaction of the various processes. So let's take heart, for example. So initially, the sinus node in the right atrium generates rhythmic excitations that define the heart rate. Then the nerve impulses are conducted by the conduction system to the myocardium. And finally, a reduction of the ventricles and ejection of blood into the aorta and the pulmonary artery occurs. So those we have three underlying processes which are excitation, conduction, and contraction, which together interact and provide the main function of the heart, which is pump blood through the vascular system. If we take kidney, for example, so we can see that the formation of urine is achieved also by three different processes: filtration, reabsorption, and secretion. Sorry. All these three functions, as a result, lead to the formation of the secondary urine. And all these examples show us that a function is achieved by interaction of various underlying processes. But why must physician know these processes? When the function is impaired, the cause can only be established by the analysis of the underlying processes. In case of the heart diseases, for example, circulatory disorder may be associated with arrhythmias as well as a destruction of the conduction system or with a decrease in myocardial contractility. Violation of each of these processes results in a disturbance of cardiac function. But all these cases require a different treatment. So now let's talk about the regulating mechanisms. They are needed for instant adaptation of the function to the changes in external and internal environment. For example, if human is in a rest state or sleeping state, his heart contracts slowly, his arterial blood pressure and cardiac output is relatively low. But if he exercises, all these indexes rises depending on his load. The nervous and the endocrine systems are two main regulatory systems that have many tools to fit the heart function to the new metabolic demand of the body. We can mention among them activation of sympathetic nervous system, the hormones, mainly epinephrine and cortisol, and many other mechanisms. About functions of these hormones, we will discuss at the end of this semester. So why should the physician be aware of these mechanisms? The answer to this question is very simple. Because the treatment of disease is nothing more than a correction of the natural mechanisms of regulation with drugs and non-drug methods. So now let's move to the next item of today's topic, which is measuring of resting membrane potential. So what is it, resting membrane potential? It is a potential difference between the outer and inner sides of the cell membrane in excitable tissues. Excitable tissues are, as I hope you know, these are nerves, muscles, and secretory cells. So if you took such a device, which is called oscilloscope, and you put one electrode at the outside of the cell membrane and one on the inside of the cell, the oscilloscope will show you the potential difference between them about -70 millivolts. At the same time, the negative charge will predominate inside the cell and positively charged ions will be located outside of the membrane. So how we can explain this asymmetry of the charge across the cell membrane? And in order to explain this, we have to discuss some features of functioning of cell membrane. First, it's different types of ion channels, and second is sodium-potassium pump. So let's start with the types of ion channels. There are two types, passive, or the synonym is leak channels, and the second one is active channels. Passive channels are always open and ions can move freely across them. Active channels have gates through which ions can move only if they are open, but most of the time they are closed because they have gates. And depending on the mechanism of opening of the gates, active channels can be divided into voltage-gated and ligand-gated ion channels. A ligand is a molecule that binds to a receptor, and a receptor is a protein that has a site to which a ligand can bind. When ligand binds to the receptor site, the ion channel opens and closes. For example, the neurotransmitter acetylcholine released from the presynaptic terminal of the neuron is a chemical signal that can bind to a ligand-gated sodium channel in the membrane of the muscle cell. And as a result, the sodium channel opens, allowing sodium to enter the cell. ligand-gated ion channels exist for sodium, potassium, calcium, and chloride. And these channels are common in tissues such as nervous tissue, muscle tissue, as well as glands. Voltage-gated ion channels open and close in response to small voltage changes across the plasma membrane. The movement of ions into or out of the cell changes the charge difference across the plasma membrane, which causes voltage-gated ion channels to open or close. This subtype of ion channels is responsible for the formation of action potential. Here you have a picture of these types of ion channels. So here you have passive channels. They have no gates and ions can freely move across them. And here you have example of ligand-gated active ion channels, which have gates, and these gates are closed most of the time and open only if there is a special stimulus. Okay, let's move next. So now let's discuss next feature of the establishing of resting membrane potential, which is sodium-potassium pump. What is it? It is a membrane protein that uses energy from ATP for moving sodium and potassium through the plasma membrane against the concentration gradients. Sodium ions are transported out of the cell, increasing the concentration of sodium outside the cell. And potassium ions are transported into the cell, increasing the concentration of potassium inside the cell. Approximately 3 sodium ions are transported out of the cell, whereas 2 potassium ions are transported into the cell for 1 ATP molecule. So the sodium-potassium pump, as you understood, creates ionic asymmetry on both sides of the cell membrane. Potassium concentration, let's look at this table. You will see that potassium concentration inside the cell is about 30-40 times higher than in the extracellular space. And the sodium ions about 10-15 times lower than outside of the cell. In the rest state, only leak channels are open and ions can move across the membrane according to the concentration gradient. Because most leak channels are potassium channels, cell membrane is mostly permeable to potassium ions that move outside the cell. However, the force of electrostatic interaction with the negatively charged ions inside the cell counteracts with potassium outflow. This force is called electrochemical gradient. When electrochemical gradient and concentration gradient become equal, a big amount of positively charged potassium ions are located on the extracellular fluid, on the outer side of the membrane. And there is an excess of negatively charged ions, mostly protein anions, inside the cell. The charge difference between outer and inner side of the cell membrane is called potassium equilibrium. And it is equal to about minus 90 millivolts. So here you have potassium equilibrium equal to minus 90 millivolts. Potassium equilibrium potential can be calculated using Nernst equation. So here you have this equation. As you see, it depends on the ratio of the concentration inside and outside of the membrane. where Ci is the concentration of the potassium inside of the cell, whereas CO is the concentration of potassium outside of the cell. However, cell membrane is somewhat permeable to sodium ions. And these positively charged ions move into the cell, positively charged ion moves into the cell membrane, into the cell, and according to the concentration gradient and electrochemical gradient, and as a result, potential difference between the outer and inner side of the cell membrane becomes -70. So let's return to the previous slide. So we said that potassium equilibrium is equal to -90 millivolts. But we said that the resting membrane potential is equal to -70. So what explained this? It's explained by the movement of the sodium inside of the cell. So positively charged sodium ions move inside the cells according to the concentration gradient, and it helps to create resting membrane potential to the -70 millivolt. So this is called resting membrane potential. The major ionic influence on the resting membrane potential is due to the movement of potassium through the leak channels. Other ions, such as the sodium, have only a minor influence on the resting membrane potential because these are relatively, there are relatively few leak channels for them. And even after the resting membrane potential is established, however, cells gradually lose potassium and gain sodium. And the large concentration gradient for sodium and potassium would eventually disappear without the continuous activity of the sodium-potassium pump. So this is how resting membrane potential is established by the help of sodium, by the help of ion channels, movement of different ions across the membrane, and the help of sodium-potassium pump, which requires ATP energy. Now let's move to the next item of today's topic, which is action potential. So when the stimulus acts on the cell membrane, it opens the voltage-gated sodium channels for the short period of time, and as a result, positively charged sodium ions, move into the cell, and potential difference is reversed. So I will recall you that previously we were talking about the resting membrane potential, and we said that in case of resting membrane potential, when cell is in the state of rest, negatively charged ions predominate inside of the cell and positively charged ions outside. But when stimulus is applied to the cell and the cell is not anymore in the state rest, then sodium ions moves into the cell, and potential difference is reversed. Now we have on the outer side of the cell membrane, we have negatively charged ions, and in the inner side, we have positively charged ions. This phase of the development of action potential is called depolarization. As soon as the difference reaches 30 millivolts, sodium channels are closed and the slow voltage-gated potassium channel are opening. At the same time, leak potassium channels remain open all the time. All these events cause the outflow of potassium ions outside of the cell and return the membrane potential to the basal level. Now, in this phase, we have again negatively charged ion inside the cell and positively outside. And this phase of the formation of action potential is called repolarization. Because of a lower density of the sodium channels compared to potassium, the repolarization phase lasts a little longer than depolarization. Voltage-gated potassium channels start closing when the membrane potential returns to the level of the membrane rest potential. But this process is relatively slow, and extra amount of potassium ions that move out of the cell creates a third phase of the action potential, which is called after hyperpolarization of this, or the second name is just hyperpolarization. An action potential occurs only if the stimulus is able to depolarize the cell membrane to the threshold level. Such stimuli are called the threshold stimuli. The threshold level is about of 15-25 millivolts lower than the membrane rest potential for most excitable tissues. Action potentials occur according to the all or none principle. If a stimulus can depolarize the cell membrane to threshold level, then the action potential with the maximum possible amplitude evolves. If the stimulus is not sufficient to reach the threshold, then action potential doesn't occur at all. The cell can't react at all to the stimuli during the depolarization phase and repolarization phase. These periods are called absolute refractory period. So here you have on this graph absolute refractory period, which occurs during the depolarization and repolarization phase. And during the after hyperpolarization phase, relatively refractory period occurs. What does it mean? It means that during the relative refractory period, cell can react on the other stimuli which are higher than the threshold, which are called supraliminal stimuli. And if we compare relatively refractory period to the absolute refractory period, in case of absolute refractory period, cell cannot react at any other stimuli at all. Next item of today's topic is graded potential. The graded potential evolves if subliminal, subthreshold stimulus is applied to the cell membrane. Only a few ionic channels are opening, and small changes of the membrane potential occur. These changes can be classified as the local depolarization and the local hyperpolarization. The local depolarization occurs if the sodium channels are opened, and local hyperpolarization if the potassium or chloride channels are open. When the strength of the stimulus rises, but still remains lower than the threshold stimulus, it's very important situation that stimulus can rise, it can increase, but it still needs to be lower than the threshold stimulus. Then the size of graded potential is rising too. This interrelationship is known as the strength principle. So graded potential works according to the strength principle. And if you compare it action potential, it works according to the all or none principle. Graded potential can spread over the cell membrane and always remains local. It's the second difference between action potential and graded potential. Graded potential can be summed up in two ways. The first way is called the temporal summation. It can be observed if a series of stimuli is applied to the cell. If temporal intervals between a single stimulus are short, then more and more channels are opened and the ionic currents arise. The second way of summation is called spatial summation. It can be observed if two and more stimulus are applied to the cell simultaneously. So now let's sum up what we were talking about, the action potential and graded potential. These potentials have quite big difference, and here you have a table of different features of these potentials. So let's briefly look on them. So graded potential can be depolarizing or hyperpolarizing, and in case of action potential, it always leads to depolarization of membrane and reversal of the membrane potential. Amplitude in case of graded potential is proportional to the strength stimulus. So I will explain again. So if strength of the stimulus rises but still remains lower than the threshold stimulus, then the force of graded potential is also increases. In case of action potential, it doesn't work according to the strength principles. It works according to all or none principle. It means if threshold stimulus is applied to the cell, then action potential will evolve with the maximum possible amplitude. Duration is also different in case of graded potential and action potential. And the ionic channels responsible for graded potential may be ligand-gated. Extracellular ligands such as neurotransmitters, mechanosensitive or temperature-sensitive channels, or maybe channels that are gated by cytoplasmic signaling molecules. In case of action potential, voltage-gated sodium and voltage-gated potassium channels are responsible for neuronal action potential. In case of graded potentials, there are no refractory periods. In action potential, we have absolute and relative refractory periods. Graded potential can be summed up, temporal and spatial summation. In case of action potential, summation is not possible. Graded potential travel by spread, electrotonic spread to neighboring membrane regions, and action potential propagation to neighboring membrane regions is characterized by regeneration of a new action potential at every point along the way. So action potential can spread to the long distances, where graded potential always remains local. Okay, let's move to the next item, which is conduction of action potential. It can be continuous and saltatory conduction. So in contrast to the graded potential, action potential can spread along the cell membrane remaining the same size. A maximal velocity of the conduction is observed in the myelinated nerve fibers. We will talk about difference between myelinated and unmyelinated nerve fibers in next slide. So in case of myelinated fibers, it reaches about 120 meters per second. mechanism of the conduction in the unmyelinated nerve fibers is achieved by the local ionic current between excited area and neighboring unexcited area. These areas have different charged because of the influx of sodium ions in the depolarization phase. The local current acts as the threshold stimulus for the next unexcited area, and the action potentials moves continuously along cell membrane, changing the charges with the neighboring areas. In case of myelinated nerve fibers, the impulse jumps from the one Ranvier node to the second Ranvier node. Such a form of conduction of action potential is called saltatory conduction. It is not only faster, but also more efficient compared to the continuous conduction, since the myelin sheath prevents the active and passive transport of ions. Therefore, the myelinated areas don't waste energy for the establishment of the membrane rest potential. So now you have here a picture of two types of nerve fibers, which are myelinated and unmyelinated, or non-myelinated, and they have some differences in the structure, which leads to different mechanisms of conduction of action potential. So in case of myelinated nerve fibers, they contain axon and myelin membrane. Surface of the axon formed by plasmatic membrane, and its content, it is exoplasma. Myelin membrane between equal spaces is interrupted. These spaces are called nodes of Ranvier. So in these nodes of Ranvier, there are no myelin sheath. It's like bare zones. Myelin membrane have two functions. First, it is trophic function, and second one is electric isolation. So as myelin membrane have lipid nature, so it don't pass ions go through membrane. So excitation can occur only at those zones, at those areas where there are no myelin. So only in the nodes of Ranvier. That's why action potential jump from one node of Ranvier to the second one. That's why propagation of action potential in the myelinated nerve fibers is much faster. And now we have last item of today's topic, features of nerve fibers. So first feature is the excitability and conductivity. What is it? It is the ability to generate action potential under the action of threshold stimulus and conduct them along the fibers. Second one, anatomical and physiological wholeness. It means that action potential can spread only in, let's so say, the healthy nerve fiber. So if the nerve, only if nerve fiber have no anatomical damages or physiological damages. Factors which can defect the physiological wholeness of nerve fibers are sharp pulling or drying the nerve, blockade of nerve using the anesthetics, and continued depolarization. Next one is bilateral conductivity. If you apply irritation in the middle of the nerve, you can register the action potential on both sides of the irritation place. It means that action potential propagate in both sides, not only in one direction. Second one is isolate conduct of impulses. So impulses spread only by certain fiber and don't distribute on the neighboring fibers, because electrical resistance of the fluid which fills the interspace between fibers much lower than resistance of the membrane of nerve fibers. So the current which occurs between excited and unexcited area of fiber goes in this interspace and don't excite the neighboring fibers. And the last feature of nerve fibers is non-decrement conduction of excitation. It means that the conduction of excitation occurs without extension. We already said that there are two big groups of nerve fibers, myelinated and unmyelinated. Except this classification, there is another one classification based on the diameter and the conduction speed of action potential. So according to this classification, we have three big groups of nerve fibers, A, B, and C. Group A is subdivided into A alpha, A beta, A gamma, and A delta. So here you have a table which explains the difference between all these groups and subgroups. So group A is subtype alpha, responsible for carrying proprioception information. It is myelinated nerve fibers. It has myelin on its structure. The diameter is from 12 to 22 micrometers, and conduction speed is from 70 to 120 meters per second. It is the most highest, this type of nerve fibers has the highest speed of conduction. A beta, responsible for carrying touch information. It is also myelinated, diameter from 5 to 13, conduction speed 30 to 90. A gamma, responsible for carrying information, motor information to muscle spindles, myelinated, it has myelinated myelin sheath, diameter from 3 to 8, and conduction speed from 15 to 40. A delta, responsible for carrying pain information, mechanical and thermal. It has myelin sheath, diameter from 1 to 5, and conduction speed from 12 to 30. Next group is B, responsible for carrying preganglionic autonomic information. It is myelin, it has myelin sheath, diameter from 1 to 3, and conduction speed from 3 to 15. And the last group is C type. It's responsible for carrying information about pain, but it is slow pain, mechanical, thermal, and chemical. And only C type doesn't have myelin sheath, so it is unmyelinated nerve fibers. Diameter is from 0.3 to 1.3 micrometers, and conduction speed is from 0.7 to 2.2. For easier to remember about features of these groups and subtypes of nerve fibers, you have this arrow. What does it represent? It means that diameter and conduction speed decreased from group A alpha to the group C. So the highest velocity of conduction of action potential is in the A alpha and the lowest in the C group. Same with the diameter. The greater diameter has A alpha type, and the lowest diameter is group C. This is how you can easily remember about velocity of action potential propagation. So this is all for today's topic. I'm waiting you at the classes where we will discuss in detail about these subtopics. So have a nice day and bye-bye.